Hi, welcome to the next week in Physics 20. This week we're going to be talking about the universal wave equation. Now, universal means that it applies to all waves, and that's what we're going to be looking at this week. Now, the universal wave equation allows us to find the velocity of a wave. Now, if we wanted to find the velocity of something that was traveling at with uniform motion, well, velocity would just be distance over time. And we can do the same thing for a wave. Now, when we talk about distance and time, there are a couple of different quantities that we use for waves. The distance traveled by one wave is the wavelength. That's the distance of one wave. Remember from last week, it's the distance from either crest to crest, or the distance from trough to trough, or the distance for the wave to start repeating itself. That's one wavelength. So if we want to find the speed of the wave, it would be the distance, the wavelength, divided by the amount of time it takes for the wave to travel that one wavelength. And if you remember from last week, the period is the amount of time it takes for one repetition. So the period is the time it takes for the wave to travel the distance of one wavelength. So velocity of a wave would be the wavelength divided by the period. Now, that's not the form of the universal wavelength. So we have velocity is the wavelength over the period. But the period, we know from last week too, is related to frequency. Period is 1 over the frequency, or frequency is 1 over the period. So substituting with what we have, we end up with this equation where velocity of a wave is equal to the frequency times the wavelength. This is the universal wave equation that we're going to be using this week. Now, looking a little closer, we can see some of the effects that frequency has on wavelength and vice versa. If we were to increase the wavelength, so if the wavelength were to get longer and the speed were to stay the same, so if the wavelength goes up, that means the frequency needs to go down. If I were to decrease the wavelength, so if the wavelength were to get smaller, then the frequency would have to go up. Now, this applies to the electromagnetic spectrum as well, where you probably listen to radio waves on your radio in your car. Those have very long wavelengths, like sometimes kilometers long, and they're at relatively low frequencies. If you look on your dial, it's sometimes like megahertz or something like that. If I were to go to a shorter wavelength, like maybe a microwave, now my wavelength is in centimeter, my frequency is going to be a little bit higher. And if I go all the way to X-rays, which even shorter wavelengths, they're going to have even higher frequencies. So we see this relationship between frequency and wavelength all the time if the speed is staying the same. Here's kind of the relationship. So if we look at frequency versus wavelength, this is an inverse relationship where frequency varies with 1 over the wavelength. And we see that graphs with inverse relationships look like this. If I wanted to get a straight line graph, so this is a straight line graph, I could plot frequency as a function of 1 over wavelength, and then I would have a straight line. So these are different lasers. Red lasers have a longer wavelength opposed to violet wavelengths, which have shorter wavelengths. Red lasers have lower frequencies, and then violet lasers have higher frequencies. Now, frequency, we learned in Physics 30, also relates to energy. So like blue and violet lasers, even green lasers can do a lot more damage compared to red lasers. Although at like when it comes to the power of the laser, that can also do damage as well. So here's a question. A wave has a frequency of 5 times 10 to the 1 hertz and a speed of 3.3 times 10 to the negative 1 meters per second. What is the wavelength of the wave? So we have V is equal to F lambda. The wavelength is lambda, so lambda is equal to the speed divided by the frequency. So my speed is 3.3 times 10 to the negative 1 divided by my frequency, and I get a wavelength of 0.66 meters. Now here's one more question. So if we assume, I don't know if you've seen Harry Potter, but maybe curses are a form of electromagnetic radiation. They have a lot of light when I watch Harry Potter. I've been watching a lot of it. Kind of having some Harry Potter marathons in the evenings. So Voldemort casts an unforgivable curse with a frequency of 560 times 10 to the 12 hertz and a speed of 3 times 10 to the 8 meters per second. So what is the wavelength of unforgivable curses? So V is equal to F lambda. Lambda is equal to V over F. So now I'm going to use the EE button because these are really big numbers. So 3 second EE8 divided by 560 times 10 to the 12. So this is 5.36 times 10 to the negative 7 meters. And then there's a question having to do with speed. So Voldemort has a very high-pitched voice with a frequency of that much and a wavelength of that much. So let's find out the speed of sound. Sound is a wave as well, and we can use this wave equation for sound also. So 300 hertz times my wavelength of 1.13 meters. So my speed of sound is 339 meters per second. And then we have this question. So Neville Longbottom is 20 meters away from Voldemort. And we want to know which one reaches him first. Is it sound with a speed of 3.39 meters per second, or is it light with 3.0 times 10 to the 8 meters per second? So does Neville Longbottom get cursed before he actually knows the curse is coming? Does the curse hit him, or does the light hit him? The curse hit him, the light, or does he hear Voldemort curse him? Or I guess I should say he who must not be named first. To do this, we can just look at our universal uniform motion. Velocity is distance over time. In this week's assignment, you'll be using that sometimes. So the time it takes is distance over velocity. So for the light, so we have light is traveling 20 meters at 3.0 times 10 to the 8 meters per second. And then we have sound, which is 20 meters at 339 meters per second. So the light is going to reach him in a time of 0.0000001234567 seconds, whereas the sound will reach him in 0.059 seconds. So light travels a lot faster than sound. In this week's assignment, you are going to be looking at some of these calculations. Some things to keep in mind: if maybe Voldemort was casting this against the mirror where you can see everything, and maybe he's 20 meters away from that. in order for that light to reach him, it goes 20 meters there and then 20 meters back. So be careful in this week's assignment when things are reflecting. You might see that from time to time in some of these calculations. But this universal wave equation, if we know the frequency and the wavelength, we can find the speed of those waves. In this week's assignment, you'll also be calculating the speed of light using a simple tool like a microwave. So if you have any questions this week, please post them in the stream, and I would be happy to answer them.